Now we're going to look at the sort of argument you make when you look at the integral from a to b of the difference of two functions, g of x minus f of x dx. This g of x minus f of x is itself a function that's being integrated with respect to x. How do we interpret this integral? Well, we can go up to a graph. Let's say that here's a graph of f of x and here's a graph of g of x. And speaking somewhat informally, if we have a typical interval delta x here, then the area under the curve for that delta x is the average value over that interval of whatever f of x is. This f av means the average over just this interval, multiplied by delta x. And of course that's going to lie between a lower sum and an upper sum, and it's going to be approximately equal to the area of the trapezoid that we get here. Similarly, g average times delta x is the area of this purple rectangle. Now notice that the purple shading goes all the way from the bottom to the top. So we multiply the average value of g average times delta x, and we get the area, at least for this integral, under the g of x graph. Again, the lower and upper sums will bound this on either side, and the area of the trapezoid will approximate it. In any case, again, note that this is a pretty informal proof. I'm not being overly rigorous here. I'm just trying to give you the idea. Your text will give you plenty of rigor when it's time to look at a rigorous proof. But the integral from a to b of g of x minus f of x dx is the limit of a sum of the sum is implicitly the sum over all the intervals from a to b of something like g average minus f average. Again, you can think of lower and upper Riemann sums converging. In any case, this integral what we're going to think of for right here as the limit as delta x goes to 0, that is, as the width of the intervals goes to 0, of this difference. Now, we can certainly use a distributive law here. G average delta x minus f average delta x, that's going to be equal to what we have here. We've done nothing except replace this expression with an equivalent expression. But then we go and we do something, well, I'm sorry, not yet, we haven't done anything yet. We take the limit as delta x goes to 0, and we note that if we add up all the g average delta x's minus f average delta x's, that's the same as if we add up all the g average delta x's and then subtract what we get when we add up all the f average delta x's. There's really no difference here. When we do this, we get a situation something like what we see here. Okay? Now, as we've seen before, the integral from a to b of g of x minus f of x dx through a bunch of equalities is the same as the sum of the g average delta x's minus f average delta x's. But now what I've done here, and what should make us a little uncomfortable, and I've done this in 2 pages, which isn't such a good idea, but if we look at what I have here, okay, we've got g average, the limit of the sum of the g average delta x's minus the sum of the f average delta x's. There's nothing wrong with this. But then we come down here and we say that this is going to be the same as the limit of the sum of the g average delta x's minus the limit of the sum of the f average delta x's. Notice we got 2 limits down here where we've only got 1 here. It's as if we've distributed this limit operation through this expression. And that should make you extremely uncomfortable because we have never proven that you can actually do that. However, for right now, accept that we can do that. It's true we can, and we'll prove it later. But after applying this, you see that the limit as delta x goes to 0 of the sum of the g average delta x's is going to just be the integral of the g of x. And the limit for the f averages is going to just be the integral of the f of x function. So that, in a sense, we have proved that this integral is equal to the difference of these integrals. The integral of the difference of 2 functions is equal to the difference of the integrals of the 2 functions.